Hi, and welcome along to a little presentation about interference and diffraction with white light. Bit of a pesky subject. Things get slightly more complicated here because we've got a range of wavelengths present. Obviously, each wavelength would need to be coherent on its own, but we're going to kind of get a mixture of the patterns superimposed on top of each other. So we'll kick off with this one. So at the bottom of the screen, you can see the patterns for three monochromatic wavelengths, red, green, and blue. Let's see if we can deduce what created this pattern. Well, what you can see here is very clearly a large central maxima, and then on either side we've got a set of much dimmer, smaller maxima. So we're definitely looking at the single slit interference pattern, aren't we? The next thing we can see is that as we go down the screen, come down to this one, we're looking at blue light, which is a shorter wavelength, and therefore the side fringes and are closer together and the central maxima is narrower. Essentially, the top pattern is all of these patterns superposed on top of each other. Just change my pen color. So in the middle here, we just get a nice white, bright white light, because we've got all wavelengths peaking in the center here. There's just a kind of glimmer of white here, isn't there? And that's because, roughly speaking, there's an area, if you look down the bottom, where the red light, the green light, and the blue light all peak together. But if we look to the right, we can see that this is tinged with blue because the shorter wavelength is on the inside, and you can see the outside is tinged with red because that's the longer wavelength, and we'll talk more about this later. But as we go further out, the pattern becomes less and less distinct. So what are we looking at here? Well, if we look at the top one, we're clearly not looking at single slit interference anymore, are we? Because what we're looking at now is a set of identical fringes. Each fringe is identical. The fringes aren't very widely separated. It kind of just about goes dark between them. So we conclude that that's a double slit interference pattern. You'll see why the small gap is significant on the next slide. Down below, we see the same slits, but we've put white light through. And we see here a pattern is emerging in that what we have in the center is white light. And what we have, either because every wavelength will be present, and every wavelength will peak at the center because all of them will have zero path difference. Again, we've just kind of got this area of white here where each wavelength will be peaking, but then on the inside we've got blue light, and on the outside we kind of get red light. Not a bad spectrum out here, but it's not quite perfect, is it? And in fact, there really isn't anywhere where there's true red light on its own. So this isn't a particularly efficient way of forming a spectrum, and the problem is that as we go further out, we reach regions where rather than just having one wavelength peaking, here we can see magenta. So that suggests that the red light of one fringe is overlapping with the blue light of another fringe. And as we go further out, you can see a general reduction in saturation going out to white light. In terms of what the exam board are looking for, and I have asked questions about this, and students in the past have found this difficult, is the key thing is the idea of the white central maxima, the first maxima on either side of the central maxima being tinted blue on the inside and red on the outside, and being able to explain that in terms of wavelengths. Finally, what are we looking at here? Well, what I was talking about before, isn't it? We've now got really significant gaps between our bright fringes, and great deal of darkness in between. There's a bit of green fuzz going on, but I think this is actually a very low resolution image which I've expanded to make it more visible on your screen. Clearly all these pictures were taken kind of before the world went HD, and certainly before it went 4K. But no, this is light through a diffraction grating, because when we get the diffraction grating, because we have so many slits interfering with each other, we properly go black between each maxima, and then we get a very bright, well-defined maxima. Underneath, you can see the effect of doing this with white light, and to a certain extent, we've already discussed this. Here is our really good spectrum. We've really gone all the way from red to blue there. Not quite sure why there's a darker band within the blue light. I suspect that's actually a quirk of their light source. Their light source wasn't quite full spectrum, or it's a quirk of their the equipment detecting the light. Anyway, here's our great spectrum, and if you ever see a discussion with a diffraction grating of what happens when light goes through and we're looking at a spectrum, it's always the first order spectrum that's used for any kind of analysis. Again, white in the center, n lambda equals d sine theta, but we can just take all of those as being n equals 0. These out here are, this is the n equals 1, and you've looked at a question previously where you've looked at the spread of this pattern, the angle between here and here, and obviously if you want to take the spectrum of something, you want a good spread in terms of angle. As we go further out, again we get this trend of the patterns being less distinct, the colors being less saturated, because as soon as we come out even to the second order or the third order, what's happening is that one color is overlapping with another color, and we've lost our distinct pattern. I think that's pretty much everything you need to know about white light interference and diffraction. So I hope you found that useful. Thank you very much.